Okay. So before we hop into our notebooks, actually, let's first pull up our. We're gonna first pull up our instances of SMCE because we know that can take a little bit to get up. So I'm gonna have everyone log into their SMCE system. So I put the link in the chat again. So everyone go ahead and log in. And again, you guys are going to select the small server on demand. So once you log in and you get to the server options, small server on demand is what you want to select. So everyone select that small server on demand and then click start. And as that's loading up, is there anything that you guys want me to go over again from the raw data QC through trimming and trim data QC that we went over yesterday and this morning? Do you guys have any questions about anything that we've gone over so far?
Amanda, if you want to clear the notebook, say you play with a notebook and you enter extra cells and you're fooling around, but you want to clear it to the notebook you created, what is the command for that?
So
Is
if
that revert?
I'll show you once this logs on. But
Okay.
if you added extra cells, doing like the clear all cells and restart kernel, which is what I'll show you, will clear all the outputs of all the cells. But if you added extra
Okay,
cells,
yeah, okay.
those cells will still be there. Just the outputs will get removed.
Okay.
If you want to start from our original files, I will
Mm-hmm.
show you how to do that
Mm-hmm.
at the end of the boot camp. So there's a few different ways you can just delete it. You can delete the notebook and then copy it from where I have the original stored, which I'll show you. Or you can just
Okay.
move everything, like create a new folder. You can even
Mm-hmm.
in that left-hand side panel, if you right click there, you can use that as a finder and create a new folder and then move all of your files into that folder and then you can run the copy command again
Okay.
initially and it'll bring up all the original files. But yeah, we'll go through all of that at the end, show you how to save all the stuff that we did now and show you guys how to start with the fresh ones. And then if you guys did make modifications that you want to keep there to teach when you guys teach at your home institutions, we'll be there. Any other questions about any of the material that we've gone over? So we are now going to be actually processing GeneLab data. So as we're waiting for these to load, I guess a little bit of background might as well. So we're going to be working with data from GLDS 104. And this link is in the Jupyter Notebook too, but mine's not up yet. So these are the data that we're going to be working with. So this is soleus muscle tissue. So a soleus muscle is one of the small muscles that make up the quadricep. And it's from the Rodent Research 1 mission. So we're going to be evaluating the transcriptome of the soleus muscle from mice that were flown in space compared with the respective ground control mice that were kept on the ground. from the very first rodent research mission. And that's what we're going to be looking at to see which genes ultimately were up or down regulated as a result of spaceflight in the soleus muscle. So if you guys want to learn more about the samples that you're working with, I encourage you to take a look at our data repository for GLDS 104, which is the link that I just put in the chat. If any of you guys got that message, yeah, ready? So mine's just about loaded now. Is anyone else still waiting for an instance to come up? Awesome. So all your instances are up. Okay. So Elba, to answer your question, if let's say you guys might still have your R or Unix intros up. Again, as a reminder, if you want to keep everything that was there from before, you want to press the floppy disk icon here to save, and then you want to go to File, Save and Export Notebook As, and then you can select HTML, and it will allow you to save this as an HTML file locally. If you want to clear all of your outputs, you go to Kernel here at the top bar, and then you want to click on Restart Kernel and clear all outputs. So that will get rid of all of the outputs that were generated in your notebook as you ran through it. However, as I mentioned, if you did add like additional cells and things like that, it's not going to get rid of those additional cells. Those you would have to scroll down to whatever cells you added that you don't want anymore, and then you'd have to hit the scissors to remove it. So you have to get rid of any cell that you don't want manually, but all the outputs you can get rid of all at the same time by going to Kernel, Restart Kernel, and clear all outputs.
Okay.
Yeah. And I'm gonna show you, I just want to do it right now, but you can like create new folders and stuff in here. So you can right click, you can use this kind of like you do with Finder on your local computer. So you can right click in the side panel and add a new folder. And then you can use, so they're like, so stuff that you did in the boot camp, and then you can kind of move. So let me X out of these first. So if I were to like X out of those, so let's say I wanted to take these and my old notebooks that already had stuff in there. And so like, I don't want to use my Unix or my R1 anymore. So you can take those and move these around just like you would in a Finder. So I could take those and pull them into the folder that I just created. And then they'll no longer be in my current directory. And then if you want to start from the original ones, I got to remember where I stored all those. So this is all on the GitHub too. So this copy command that I have you guys run here, right at the top, this is like the location in the system where everything is. And you guys all have access to this, so you know, be careful. I do have backup copies. You guys don't have to do this. I'm trying to remember where my stuff is. Okay, so I just removed my 2 intro notebooks. So if you guys want to recopy, so let's say that you did what I just did and you took your R intro and your Unix intro Jupyter notebooks that you had here on your left panel and you made a new folder and you put them in there. You can copy the original ones back by running this command in the terminal. So you can open up a terminal and then run this command. I'll copy and paste this in the chat. So if you wanted to start with the original Unix one, you can run this command here. And that command will copy the original Unix Jupyter notebook that we all started with. So if you guys added any additional cells or anything like that, those will no longer be there. And then, of course, what does this tilde indicate?
Directory, home directory.
What directory?
Home.
Home, yeah. Sorry, might have said that. So yeah, so your tilde indicates your home directory, which is what we're looking at here. And so you can run this command. Keep in mind that if you did not move your Unix Intro Jupyter notebook from your home location before running this command, it will overwrite that notebook because it has the same name. So that's why if you do want to start over, if you don't want to lose what you had done originally, make sure you make a new folder, move it into that new folder so it's no longer in your home directory. And then you can run this command. And then what you'll see is that will populate. It eventually come up in there. Yeah, there it is. So you see, I just got it populated with my Unix intro. You can also run ls tilde to view what's in your home directory, and you should see that Unix intro then populate in your home directory. Again, if you ran that command before you moved your original Jupyter Unix intro Jupyter notebook that we were working on, you will have overwritten what you had there already. So just be careful about that. Yeah, and we'll go over all this a lot the last day of the boot camp, so that way you guys can know how to move these files around, save what you've done so far, and still be able to populate new files. We can create, if you guys have unique Jupyter notebooks that you've added to, we can create locations for those, so you can use the ones that you specifically modified in your courses. So at the end of the boot camp, we're going to go over all that to make sure that you guys have everything you want when you teach this at your home institutions. Just going to go back to my home directory, and we don't need the terminal for this. So we are going to now start processing data. So I want everyone to open up their RNAseq FastQt accounts JN, this one right here. Copy. Copy. I think I copied the whole file there. Yeah. Does anyone not have this up? Okay, great. So you guys are all seeing what I'm seeing here on the right? Okay, in that case, I'm going to move my left panel over so you guys can see this more. Okay, so as I mentioned, at the beginning, this Jupyter notebook was built originally in collaboration with San Jose State to teach everyone how to process RNA-seq data. Oh, thanks, Lauren. Yeah, so as Lauren pointed out in the chat, this kernel should be running the Python. So if you look here down at the bottom, the Python conda environment GL4U should be the kernel that you guys are running. Is there anyone not seeing this kernel on their instance? Okay, good. Let us know if that goes away, ever. So here we have step-by-step instructions for processing samples, as I mentioned, derived from the soleus muscle. This is also commonly referred to as the anti-gravity muscle because it tends to be the muscle most dramatically affected by changes in gravity. And the muscle and the muscles that we're going to be assessing were either flown in space, as I mentioned, aboard the International Space Station, or they were kept in an environmental simulator on the Earth to serve as our ground controls. And that was all during the Rodent Research 1 mission, which was conducted in 2014. And for more information about the samples, you could look at the GeneLab data repository under specifically GLDS 104. And so those should link you out to the link that I put in the chat. And then here we have similar to in the lecture material, but a bit more expanded out. So this is the workflow that we're going to be doing in this Jupyter notebook. And so each one of these numbers corresponds to a section in the notebook that you can find in your table of contents. So we start with our raw reads, and then the first thing we're going to do is evaluate the quality of our raw reads, similar to what I showed you in the lecture. And then we're going to trim or filter those raw data, and then we're going to check the quality again. And then once we have those nice and clean, we will be generating a star index. Actually, you'll be using the star index that I generated, which we'll talk about. And then we'll align or map our reads using the star program. And then we're going to check the quality of those aligned data using multi-QC. And then we are going to index those aligned reads, and I'll go into detail about what all these things mean in the lecture. And then we're going to create a bed file, which is needed for this next tool called RNAseq and for experiment to determine the strandedness of our reads compared to our reference. And then we're going to compile those for all samples with multi-QC. And then we're going to create an index for our quantitation tool that we use, RSEM. And then we're going to use that quantitation tool to count all of the reads aligned to our genes. And then we're going to compile that quantitation information, again, using multi-QC. And then we'll be ending this notebook by putting the raw expression data from all of the samples together in one table. And that will conclude this, this part of the pipeline. And then I'll be handing you guys over to Lauren for the rest. So again, you'll see the numbers in the corner of all these. They correspond to the section in the Jupyter notebook. So we're first going to go over the 2 steps that we discussed in the lecture. And so again, you can hop around as needed using these links. They're all connected. And so if you go to the end here of the table of contents, or if you just click on this 0, it'll bring you to the first thing that we're going to do, which is create a directory structure. So yeah, if you have to restart your kernel, run the code block. Okay, so if we get into the point where we have to rerun the kernel, we're going to have to rerun all the code blocks that we're going through right now. But before we get into that, let's do this, and then I'll show you that again. So before running any analyses, we're going to create a directory structure to store the data. So as we process RNA-seq data, we're going to generate a bunch of files, depending on how many samples you have. You could generate hundreds of files when processing RNA-seq data. I am a huge stickler for organization, so it's really important to keep those QC and process data files organized so you know where to find everything. And so we're going to start first, before anything else, by using that make dir command that we went over in the intro Unix Jupyter notebook to make a directory structure for us to output all of our process files into. And so as I mentioned, this is going to be a bit more structured than the Unix intro where you guys were inputting commands. I kind of pre-populated these with the commands that you'll have to run. So it'll be a little more straightforward for just running these commands. But you guys all know what these do, so we should be able to take a look. So we want to go ahead and run this first cell, which is make our top level directory. So again, you can press the play button up here, or you could hold shift and enter when you're in a cell to run that cell. You won't see any output right here. However, if you look to the left, because you just made your directory, you should see that directory being populated here in your left-hand panel. You could also, as we know, if you wanted to add a cell and run your ls command to look at what's in your home directory, you should also see that GLDS 104 directory that you just made in there. Note that when I process data for GeneLab, I always do the top level directory is the GLDS number. Okay, so Kanisha's not seeing, you're not seeing the directory populated on the left panel here?
Do that again. Sorry.
Yeah, no problem.
I'm not seeing it. It didn't populate in mine. It says the directory exists, but
yeah,
it's not there.
There is a lag for when you see it in here, but first, just to make sure everyone's in the right place, go ahead and add a code block and let's run that pwd command. So I want everyone to add a code block and run pwd and make sure that you're in this location, /home/Jovian. I think I was pronouncing that wrong. Mike pointed that out. Is that how you pronounce it, Mike? Jovian?
Yeah, it's a made up word, anyway, a newly made up word. It's just I'm misspelling Jovian moons with a Y like they do with Jupiter. But yeah.
Is there
That was a
anyone?
private note. Now you make me sound like a jerk. I don't care how you say it.
No, I think it's important to pronounce things the right way. It never offends me. Like I want people to correct me when I pronounce things wrong.
I'm not in that one. I'm in some EFS directory.
Okay.
I see everything, but I don't see the other stuff. I mean, I see all the other ones, but I just don't see that one. I'm in an EFS directory.
You're an EFS? Yeah, so we want to make sure that everyone's in their home directory. So I want everyone to add a code block. Do you guys remember the command to move throughout your file system, the command and change directories?
Moving up and down. CD,
C CD,
Sorry,
percent.
percent
Amanda.
CD.
Percent.
So,
Okay, sorry, Amanda, sorry, quick
yes.
question. So, okay, after table of, can you go back up? After table of contents, right?
Mhm.
All right, scroll down. Keep going. Right, so you see you have 0 dot create directory. Mine says 0 dot load our libraries. Am I in the wrong place?
I think that you clicked the wrong Jupyter notebook.
Okay. Woo. Wait, wait.
Let me, you guys don't have to do this, but I just want to make sure that I can copy and paste the.
Okay, hold on. Okay, wait. Yes, this is the right book. Sorry, people.
No, you're fine.
Okay, good. All right. Think I got it.
I just want to make sure. Oh, here it is. Yeah, so this is the notebook here. I'm going to copy and paste this in the chat. So this is the notebook that you guys should all need to open. So double click, make sure that you guys are running that notebook, RNAseq fast-queued accounts JN 06 2022. So yeah, make sure that you guys have this correct notebook out. Elba, when you were playing around in the terminal, probably following along with me to show you how to copy a new blank file, you changed your location, and so that's
Yeah. No, that's why I wanted to clear. I was playing around. No, I'm back. I found it.
okay.
Thanks. It's, yeah.
Okay, great. Yeah, so I want everyone, just in case, everyone add a code block and run %cd with a tilde, and that will bring you back to your home directory. And then add another code block and do !pwd to make sure that you're in your home directory, which should be home Jovian. Is there anyone who's not here when they run pwd? Okay, so everyone's in the same location. So now once you're here, if you weren't here before, go ahead and rerun that first block that's mkdir. Current directory name that we want to make is GLDS 104. So you want to go ahead and run that if you haven't already. You can run it a second time because it won't, it actually won't make a directory name if the directory already exists. And then you guys should see in your left-hand panel, a directory called GLDS 104. Is there anyone who's not seeing that?
I have a bit of a side question, if that's okay.
Sure.
If I were to explain what a directory is to potential future students, how would you describe it in the simplest terms?
Honestly, what I would do is I would go to my local computer and I would have them open up a Finder window. Because most people are used to this, right?
Right.
Nowadays, most people are used to this. And I would say, you know how when you go to your desktop, for instance, and you, if I kind of move these over real quick. So just like most people know, right, going to their desktop, they know they can right click and click new folder.
Yes.
And they can name that folder whatever they want. And then they can then go to a Finder window, see that folder's there, double click in it, move files in and out of it. So that's what I would say. It's just a system to organize files on a computer, just like a file system, just exactly your file system in your computer when you use these GUIs, these graphical user interface. So just like when you use Finder and you see your folders listed, it's the same thing when you do the make dir.
Thank you. I think that's really straightforward. Thank you.
Yeah, no problem. Okay, so everyone should be in your home directory. You guys should all see GLDS 104 directory made on the left-hand panel. Is there anyone who does not see that? Great. Okay, so we've made our top level directory. And now we're going to make a whole bunch of subdirectories to organize all of the output files for the different levels of process data. So just quickly up here, just scrolling back up to this workflow diagram, we kind of have like different levels of process data here is how I like to think of it. So we have our raw data, right, which will be our raw FASTQ files. And then when we run FastQC, we're going to have those quality files for the data in there. And so I kind of like to make a subdirectory under that main GLDS 104 directory for each level of process data. So I'll make one for our raw data, and it'll be the actual raw data FASTQ files as well as the quality control files. I'll make a directory for my trim data. So then everything involving my trim data would be in that directory. I'll make another directory for alignment data and another one for count data. So that's pretty much what I've set up for you guys in these code blocks here. So I make within my GLDS 104 directory, I want to make a new directory. And I always do levels, so 0, 0 is like the starting point, and then I do 0, 1 because that's the next level, 0, 2 is like the next thing that you do in the step. And then I have this directory for like just quality control analyses that we do on the alignment data, and then I have the next level, the processing 03. And then the final level that you guys are going to do with Lauren is normalizing and doing your DGE. So I like to make all those directories right up front. And so that's what we're doing here. And remember, in each code block, you can run multiple commands in the code block. And when you run that code block, it'll run each command one at a time. So what this is going to do is it's going to make a directory within the directory that we just made, within this GLDS 104 directory. It's going to make a subdirectory called 00-raw data. And then it's going to run this command down here, which is going to make a subdirectory within my 00 raw data directory called FastQC reports. And that's where I'm going to output all of our FastQC results from all of our samples. Because remember, we're going to get files from each sample. So we have 12 samples, 6 flight samples, 6 ground control samples. And so minimum of 12. And then if there's tools that will produce multiple files, as we'll see. And so there'll be a set of those files per sample. So that's why we get so many files when we process RNA-seq data. We are creating these subfolders for all the data. Yes. So it is better to have the organized earlier on. Yeah. I like to make all of my folders right up front. Again, this is a personal preference of mine. It's anyone who works with me on the data processing team will tell you I am very crazy and anal about organizing things and organizing things in a very consistent manner. So this is the organization that I've set up and that I make everyone else use too on the team. Thanks, Mike. And so we're going to create a subdirectory for our FastQC reports for our raw data. And then within there, if you'll notice up here, I have a FastQC multi-QC. So I think I mentioned this maybe yesterday, that we have this multi-QC tool that is really good with combining information in files from multiple different samples. And so in the FastQC reports directory, I'm going to have the individual outputs from each individual sample. And then I'm going to run this program, we're all going to run this program called multi-QC to compile all of that information from each sample into a new set of output files that'll have everything there in one file. And so I kind of wanted to separate that out. So I make another subdirectory called raw multi-QC report. And that's where it will be the compilation of all the individual sample FastQC reports. So if you haven't done so already, go ahead and run that. And then if you're ever curious, just to show you what this looks like, actually let's do it at the end. I'll show you what it looks like in here at the end. And so the next that I'm going to do is create another directory for within GLDS 104, so within that top level directory there that I created. I'm going to create another subdirectory at the same level as raw data, but this one's going to be called 01. And then I have this abbreviation TG underscore preproc, and the reason that I use that specific abbreviation, 01 meaning that it comes after raw data, it's the next step, a dash just as a separator, because remember, spaces are bad. So whenever we're naming files or folders, we do not want to use spaces. TG is standing for trim galore. So trim galore is the tool that we use to do the trimming. And so it just reminds me that these were pre-processed, which is what pre-proc stands for. They were pre-processed with the trim galore tool. As we enter these commands, you can literally see, yeah, that's what I was going to show, Chief, yeah, at the end there. So this is going to be the top level directory for all of our trim data. And then I'm going to make some subdirectories within here. So I'm going to make a directory where it's going to hold the new FASTQ files, right? So remember, we give the trimming algorithm the raw FASTQ files containing all of the raw reads. And then the algorithm, once it goes through and it does all the quality trimming and it removes all the adapters, it's going to have a new set of FASTQ files that are going to have some of those reads that got too short. Those are going to be removed. So the output of the trim galore is to be a new set of FASTQ file for each of your samples. And so I'm going to put those trimmed FASTQ files in this subdirectory called FASTQ. And then we're also going to run quality check on those. So I'm going to make another subdirectory within my O1TG preproc directory called FastQC reports, similar to the raw data, and that's going to hold the FastQC reports for the trim data. So again, we're going to do a quality assessment there. And then we're going to compile that FastQC quality assessment for each sample all together using multi-QC. So I have a subdirectory within the FastQC reports called trimmed multi-QC report, which will contain all the compiled information. So you can go ahead and run that if you haven't already. And then I think you guys get the idea of my directory structure, so I won't go through that in painstaking detail for every single one of these, but I pretty much follow that same kind of mindset here and go through and make directories for each level of the data and subdirectories for any additional QC reports and stuff like that. So you guys can go ahead and run each one of these. So this is going to be for all the alignment level data. And then if you remember, we need to do some checks on that aligned data. So one of the things we have to check is what is the orientation of the read relative to the reference, because we need to know, if you remember in the library prep, we use a stranded kit, which means we maintained the strandedness of our original input RNA. And so we need to know what the orientation is that we had maintained relative to the reference that we're using. And so it's a type of QC analysis on the alignment data. So I make a level directory called RCQC analyses. RCQC is the tool used to do the strandedness assessment. And actually, we're not going to do it here, but for our standard processing pipeline in GeneLab, I do a bunch of additional QC analysis using this RCQC. It's a tool suite, so it has a bunch of tools in it. And so because of that, within this RQC analysis, I have the infer experiment, which is the one to assess strandedness, and then we'll compile all of those from each sample into a multi-QC report again. So that's why this one's kind of a little different than the other ones. And then after that, the next step after alignment would be to do your quantitation. So this is the directories for quantitation. And then after we do our quantitation, we'll have raw count data. And then I believe Wei-Jin pointed out that we then have to normalize our raw data. And so I have another directory here where we'll be normalizing all of our expression data to account for differences in read depth and RNA complexity, which we'll get into later. So we'll go ahead and set those up right at the beginning too. And then last but certainly not least, ultimately our differential gene expression, which we do, which is abbreviated DGE. Which we do with a DE-seq2 algorithm. We also use DE-seq2 to normalize. So go ahead and make those directories. And then as Chief pointed out in the chat, this brings us to the end of our directory creation. We only have to do this once. Now when we log on each day, that directory will continue to be in our home folder. And so if you guys are curious what you just did, you can kind of look over here on the left and double click into that GLDS 104 directory. And now you can see all of the top level subdirectories. Well, I guess directly under GLDS 104. They do, I think in coding, right? They call it like parent directory, child directory, grandchild directory, right? I think, I don't know if there are any developers as our instructors, but I hear it referred to as that. So if GLDS 104 is our parent directory, these are going to be all of our child directories here. And then each one of these child directories will have grandchild directories. And then some of them, like raw data, will have a great grandchild directory here, kind of going through the levels. and you can navigate back and forth up here if you want to. So if you want to go back one, you can. I'm going to go back again to GLDS 104. You can go in here and then you can kind of see the levels, right? So for 01, we did FAST-Q and FAST-QC, and then in there is our terming report. So that's kind of what we were doing when we were running all of these commands. This is what it looks like in a nice little Finder-esque type of view. If you guys have been looking around in here, just go ahead and click your home folder at the end, because we're going to be adding some files now to our home directory, so I want you guys to be able to see those. So make sure that up here your path is just this one folder with a // that's your home directory. If it's not, just click on that first folder and it'll bring you back there. Is there anyone that's not back to their home directory? Okay, cool. So the next thing that we're going to do is, if you guys remember when I had talked about this originally, is that some of the steps, a lot of the steps actually, in processing RNA-seq data take time. So it's going to take time to run, and how much time depends on your compute resources. So Chief has a question here. Depending on where you are on the left-hand side, does that impact where you are in the terminal? No, it shouldn't. You can always check that too. So if you're curious about this, so if you add a new launcher window, again, you could do that by clicking the blue plus sign here and then scroll down to terminal. You could also do that in your Jupyter notebooks, which I'll show you in a second. So you can see where you are. Here's in a terminal, so I don't need an exclamation point. It's already running Unix. So I could do pwd, and I see that I'm in my home directory, right, which matches where I am here. Now if I navigate here to GLDS 104, and then I go back to my terminal and do pwd, I'm still in my home directory. So this won't affect where you are in here. So you can play around in here. The only thing is that you won't see. Yeah, it doesn't do that. But and then of course you can add a cell here, and then this is where you'd have to do an exclamation point pwd, and you see that it's still saying I'm in my home directory, even though you can see 104 here. So these kind of you're not going to affect what you're looking at here.
I have one more question. Sorry about that.
No.
So literally the next code that we're about to enter in, like the this one that has a wall of text. In our case, this has already been prepared. But I'm assuming if we were to set up this code ourselves, we would have to type in each of these lines manually, right? Like the next one, the defining the paths to the process data. So we would have to enter each of those addresses manually. But that sounds pretty tedious, though.
Yeah.
Okay, I just want to confirm. Okay, I don't want to be missing
It's
anything.
a lot of money.
No, I just wanted to confirm because it seemed like it's a very tedious thing to do. But as long as I'm aware, then that's no problem.
Yeah.
It's
So
also, like, Amanda's keeping things less complicated where possible, but you'll notice there's the same large extension before all of these. It's like EFS, GL4U, blah, 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 blah. If we wanted, we can make that its own variable, and it would be much shorter to set all these further ones. But we're, intentionally not overcomplicating things as we go. But there's almost always ways to make things easier if you really want to pursue them rather than doing things manually.
Thank you. Yeah, I was about to say the same thing. Like some of these things could be copy and pasted, but I'm assuming that attention to detail is also very important. You don't want to copy over something that doesn't need to be copied over.
yeah, and especially, right, like, because I've seen this too, as someone will use the same string in a script that they're writing, and if they have a typo in that string and then they copy and paste it in multiple locations in their script, nothing will work. So there's also that. You got to be careful when you're doing copy and paste to like make your scripts. Yeah. So this next code block here, which I know looks like a lot, this is something that we all did our intro to Unix notebook. So as I mentioned before, because each step of RNA-seq is going to take time to process, especially if we're doing multiple samples, right? So we have 12 samples total here, 6 from our flight animals and 6 from our ground control animals. And so in order to save time, we did some cooking show magic. So you know how you're watching a cooking show and they add all the ingredients and show you how they do it, and then they're like, and then put it in the oven for 2 hours, but then magically they have one already done. This is the magic that we're doing. So I've already processed all of the samples all the way through, and so rather than us all having to wait for all of our jobs to finish at every single step before moving on, we're going to take a look at the output files that have already been generated. It's just so that way we don't have to wait for your stuff to finish. And so because of that, this code block here, all that it's doing, each line is making a shortcut to a different level of data and data that's already been processed. So just like in our intro to Unix Jupyter notebooks, where we made shortcuts to like our home directory and our solar system directory, all that we're doing here is making a shortcut to the directories containing the data that I've already pre-processed. And so right here, and I tried to create aliases that are going to be or variable names, I should say, that are going to be easy to understand. So this variable name here is going to hold the path to where all of the raw FASTQ files are. This variable here holds the path to where all of the outputs from the FASTQC analysis or the quality control check on that FASTQ file. This is going to hold the output from that multi-QC step that we're going to run, the outputs from trimming, the outputs to all of our trimming reports, etc. So each one of these, all that we're doing is setting up variables to indicate a path to where the process data files are. So that way, when we want to look at those process data files, to what Mike pointed out, we don't have to write out all of this. We can just call our variable. Do you guys remember how we call variables in Unix? What do we have to add in front of the variable name? So echo is to know what it is, but what if we actually want to use the variable? What do we have to put after echo? Yeah, the $sign. Exactly. Yeah. So you'll notice that when we're trying to look at files that are stored in these locations, we're going to call them with this name, but with the $sign in front, which is going to tell it, hey, look inside this path. And so, again, I put all of these in one code block so we can just make all of these variables at the same time. And so we can go ahead and press play there, and it should end pretty quickly. And just to kind of prove to yourselves that we actually did something here, so now you can use the echo command that Susie mentioned. Again, put an exclamation point in front. So echo, and then we could just pick one of these. If you want to echo the raw FASTQ, you can copy that, and then we call, oops, sorry about that. We call that with the $sign, raw FASTQ. And what we should see is exactly what we defined it as, right? So that matches exactly what we defined it as up here. And we just made variables for all these different levels. So if we want to know, oh, where is the aligned multi-QC data, we could just replace that variable name with that. And that should match the path that we told it to find those stuff in it. So that's all that we're doing there, is just defining paths to the process data files. That way we can all view the same files and not have to wait for people's things to finish. That said, what do you guys remember about variables? Are they permanent? Will they go away ever? Variables, permanent, not permanent. Temporary for the instance, yes. So if it so happens that during our breaks, or even if there's a glitch in the system and we see that we no longer have our active kernel here, if somehow our kernel got disconnected, what we're going to have to do is we're going to have to rerun this before we do anything else to make sure that all of those variable names are set. And so that's what that comment was up here that I noted. So just to make it easy, right, because we might be like all the way down here and then you realize that your kernel restarted. So anytime that happens, I made a shortcut to that section. So you can just start at the top here, and if your instance is restarted, you could just go down into this 0 section and click here, and that'll bring you to this part of the notebook, and then you would just rerun this code block. So again, if any of your instances get shut off, you would just have to come to this code block and rerun it before you picked up where we are. Okay, so now we have made our directory structures for where to output all of our files when we do our processing. We have defined paths, so that way we don't have to wait for things to finish and we can view process data that I already made. And so the next thing that we want to do is there's going to be some files. There's a glitch in viewing HTML files within a directory structure for some reason. I don't really know why. But because of that, it seems to want HTML files to be in each individual's directory. And so the HTML files that we're going to be viewing, if you guys remember in the lecture here, when we went over these FastQC reports, these are all in HTML format. So we're going to view FastQC reports that we generate. And so in order to view them, we need to copy them to our home directory. And so we all should be in our home directories right now. So maybe before we run this, let's all just do a check again, just to make sure that you are indeed in your home directory. And then once you confirm that you're in our home directory, you can run this next code block. And what this does is use the CP command. Who remembers what the CP command is? Put it in the chat. Yeah, copy. So all that we're doing here is we're just going to copy the HTML files that we're going to view in subsequent sections to our home directory. Again, just a weird thing. For whatever reason, viewing it using the path is, I don't know, weird with HTML files. Haven't really figured out why. I don't know, Lauren, if you've ever figured out why that is. I know you're looking into it a bit more.
No, I never did. It is still a mystery.
So we just did this workaround where we're just going to copy these files into our home directories right off the bat. So you guys can go ahead and run that command. And what you should see after it's done copying. And remember, you know that it's done because it'll be populated with a number here in the brackets next to the code block. So that's how you know it's done. If there's a star there, that means it's still running. And so once that completes, what you should see on your left-hand panel is that you have just added a whole bunch of these files that end in HTML. So all these HTML files we just added. And so we're going to be viewing those from our home directory during the bootcamp. Is there anyone who did not finish this run yet to copy their HTML files? So is there anyone who's not seeing these HTML files in their home directory here on the left panel? Awesome. So everyone has them? Wonderful. Okay, that's pretty much all of the housekeeping, right? We got our directory structure set up. We've built all of our variables to go to paths for files that we need. We've copied over HTML files that we're going to be viewing into our home directory. So now that we've done all that kind of housekeeping stuff, it's time to start processing our RNA-seq data. And so some of this is going to be redundant from the lecture. Redundancy is a good thing. It helps us remember things. So we will go through all of these again. But if you notice that it's going too slow for you, please let me know. Because if all of you guys are like, I get it, let's move on, I can go faster. Or I can go slower. So just let me know. So first, we're going to start by taking a look at our raw reads from our data using that FastQC tool that we kind of went over the outputs from. So if you guys want to learn more about the FastQC program, this links out to the FastQC documentation. So you can learn more about FastQC. What that tool does is has extra links to additional documentation information about the tool and its functionality. I have that for any program or tool that we use throughout. I have links to the documents for that you guys can view. So as we mentioned during the lecture, short read sequences data are going to be stored in FASTQ files, which contain several, often millions of reads. And each read is going to consist of the following 4-line structure. So just another reminder here, just like it's written in the lecture, I also have it written here in the notebooks. Line 1 is going to begin with an @ sign, followed by that information about the sequencing run, such as the sequencing platform, run number, flow cell ID, cluster location, read number, sample index. So this is just the example from the lecture here again. Line 2 is going to contain your nucleotide. So what you just sequenced is going to be in line 2. Line 3 is going to be your separator line, often has a plus at the beginning of it, but not always. And then line 4 is going to be your quality scores for each base in line 2 in your sequencing line, in your sequence line. So FastQC is going to basically compile this quality information from each one of the reads for each of your samples and generate a summary report about the quality of the sequence data. So assessing the raw sequence quality is of course important for determining if and how the reads need to be trimmed. So the first thing that we are going to do is run FastQC on the forward read of one of our flight samples. And we're going to do that using this command. So this is the FastQC command that we're going to be running. FastQC can take, it's pretty quick, but it still is at least a few minutes to run. And so I didn't want us to all have to sit here and wait a few minutes to run this for everyone. And so we set up a script. And so if you guys recall from the intro lecture, the last thing I did was went over these Slurm array scripts. And this is when you want to submit a job to a compute cluster. So we have kind of like a simulated compute cluster set up. So that way, rather than running your jobs directly through the notebook, which is what we did with the Unix commands, we were running things like directly on our notebook. What you can do is submit jobs to a job scheduler in a cluster scenario. So if you work in an institution, you have a compute cluster there, you would have some sort of job scheduler. And so you would submit your jobs to the job scheduler, and that job scheduler would assess all the compute resources available. And then if there was enough compute resources available, it will run the job. If there's not enough compute resources available, it will put your job in a queue. And then once there is enough compute resources available, it'll run your job. So that's how we're going to be setting up, how we're going to be running our jobs is by submitting them to our simulated job scheduler. And just before we get into running that script, the first thing that I want to do is tell you guys about this command. So this is the FastQC command. So similar to all other commands that we are running in Unix, we start with the name of the program here. So FastQC is how we call the FastQC program. And then we have this -O. What is that? What is that with respect to like type the structure of a command? Unmute your mic, type it in the chat. You don't have to tell me specifically what -O means, but just, yeah, it's a flag, right? Right, yeah, it actually is, Susie, a flag that indicates output. So this is just a flag, it's a parameter that we can use from the FastQC program. And this one happens to instruct where to output the files that are generated when you run FastQC. If you did not know what that flag meant, how would you find out? How do you find out the different options of tools in Unix?
--help.
Yeah, --help. So if you guys wanted to, you can go ahead and add a code block here, and we could do an exclamation point, FastQC, --help, and run it. And what we'll see, put this in the chat here. So you guys can add a code block and run this command. And what you see is it tells you, you'll see the developer wrote this a little nicely with more separation here. So FastQC, what it is, and output a high throughput sequence QC analysis tool. The synopsis tells you how it's run. So it can run with FastQC and then just your files. However, there's some optional options. And remember, optional options are indicated with brackets. And so here's the description, more thorough description of what FastQC does. And then here's all the options for the programs. And so we want to, the -O option that's in the command above will create all output files in the specified output directory. So this is to specify the output directory. And again, this is so that we're not just putting everything out right in the directory where we are. We just set up this wonderful directory structure to keep these outputs organized. And so we want to specify the tool, hey, put the output for this tool in that directory that I made for this part of the analysis. And so that's what you'll notice here is that we have FastQC and we're telling it to output into this directory that we just made up above, right? So into GLDS 104, into the 00 raw data subdirectory from there, and even further into the subdirectory for the quality control reports. So we're telling it to output those reports into that location. And then you'll notice that we're calling one of the FastQ files here. There's nothing before it. So which type of argument is this? Anybody remember? Mike, you're cheating. You're an instructor. So Mike gave you all the answer. This is considered a positional argument because we didn't have to add a flag to it. So again, if you go to the help menu here, it'll tell you that it expects at the end of your command, probably more explicitly here. So this is how you would set it up. FastQC, you can choose to add any one of these optional flags if you want to. But then you have to have, right, this isn't optional, it's not in brackets, you have to tell it what file to run the FastQC program on. And so we want to tell it is what FastQ files to run on. And you'll notice here that you can put multiple FastQ files at once and it'll output a report for each one. And so, where was I up here? And so basically this is telling it to work on the FastQ file that's inside the directory held in the variable raw FastQ. If you guys want to remember, I'm going to hide this for now. If you guys want to remember what was in the variable raw FastQ, add. And we can use our echo command like we did above. Make sure I put an exclamation point at the front. So it's going to tell it, right, to look at this path and to use the file. And if you guys remember, variables that are held within an array script are going to be special. And you indicate that it's a variable for the array with brackets. So that was, if you guys remember, me going over the array script, what we saw here when we had a file with a list of samples. Each sample is on one line, and we store that in a variable called sample, but it's going to be associated with an array ID. And so the number of jobs in the array is going to be indicated in the slurm option -- array. So in our case, we're going to have 12 samples, and we're going to view this script on our system, so 1 through 12. And then those 12 jobs are going to be associated with each of the 12 samples that we have stored in a variable called sample, and that variable is going to change depending on which job we're running, right? So we have 12 jobs. We're going to run that same FastQ command on each one. The difference is going to be the sample that it's running on. And so because this variable here is going to change based on which job ID we're running, it's kind of like a special variable. And so to call that changing variable in our command, we have the $sign still, but then the actual variable name we put inside brackets, curly brackets. So that's what that is. And here is just the name of the sample. And then this information is the rest of what the file is. So this file is going to be the sample name _R. And then this star here is a wildcard. So it's basically saying run this on all files that start with the same sample name, have an _R, and then anything can come after that R. So that means that it'll run it on both R1 and R2 for us because we have paired end sequence data. And the end of that file should end in _raw.fastq.gz. And so to show you a little more about what that looks like, how can we look to see what files are in this directory? What's the command for that? You guys remember the command to see what files are in a directory? Yeah, Ty, ls. Yeah, so we can run ls. And then we can run that variable name. And again, that variable is just indicating a path. And so when we run that, we'll list all the files that are in there. And you'll notice, again, to save money, it costs money to store files in the system. And so I only stored 2 files that we're going to be looking at during the bootcamp. But in reality, if you guys are processing a data set at your home institution, you, of course, would have all of your raw FastQ files in there. And so these are just the 2 that we're going to be looking at. So you'll see it there. And so what you can see is that we have the sample name. Let's see, I put that. So we have the sample name. So in this case, this is our flight rep1 sample, right? See how it matches that? Then I have an _, which matches that. And then I have an R, right? So again, matches that. And then we have a wildcard here. So that means It can be anything that comes after R so long as it ends in underscore raw.fastq.gz. So that means that we'll have this and this both have the same exact sample name with the R, and then you'll see there's a 1 and a 2, so that's why there's that wildcard there. So it'll run it on both our forward and our reverse read for each sample, and then these both end in underscore raw.fastq.gz. So it's going to run this fastqc command on both of those files in the one command. And then for each one of the commands, I won't like go through this much detail with all the commands, just because this is the first one. I want you guys to know where all this stuff came from. And so the other thing is you can, of course, look at the documentation for FastQC. You could look at the help menu to see what these parameters are. But just for your convenience, so that you don't have to go to a million places to find out what these are, I have for each of the commands that we've run a list of the parameter definitions. So again, you can pull this information up using the help menu. Just that we don't have to do that, I have those listed here. So this -O is going to indicate the output directory to store the FastQC results. And then you'll notice the things that anything that ends in fastq.gz, so a wildcard in computer language means anything. So anything, as long as it ends in .fastq.gz, is going to be the input reads. And I can tell you here that they're specified as a positional argument. And they can be given all at once with wildcards, or they can be given as individual arguments with spaces in between them. And so we kind of have a wildcard here to do both the forward and the reverse read for this one sample, which is stored, the sample name is stored in that special variable sample. And then I also have listed for all the jobs that we're going to run is input data. So what data do we need to provide to this tool in order to run? So our input data is going to be the files that end in raw.fastq.gz, and I just have in parentheses here what those files are. So those are our raw reads. And then I have a list here of the output data we expect to get back from this tool. Again, you can find all of this on the tool documentation. So this link here to the FastQC program, it'll tell you all the output files that you have and give you some information about how to interpret those output files. So here's just listing the output data that we expect to get from this tool. So we should expect to get a file that ends in fastqc.html, and that's going to be the FastQC report in HTML format. So it's essentially a web page file containing graphical representation of the raw sequence quality. We're also going to get a fastqc.zip file. So this is going to be a compressed directory that contains all of the quality reports of all the raw sequence data assessed. So this HTML is going to be that nice graphical stuff that we were looking at the lecture. How it got all the data to do that graphing is going to be stored in this zip file. Any questions about the setup of the command or this structure? You're going to see this structure repeated for every single step. So, okay, good. And so before we submit this script, and again, we won't do this with all of them, but just for the first one. So this is a script that we're going to be running. And I want to view that script. What command do I use to look at a file? Type it in the chat, unmute your mic. Head is to look at the top of the file. That's true. What if I want to look at the whole file? You guys remember that command? It's on the screen. Give you a hint. Yeah. So head is if you want to look at the first few lines of a file, but the cat command is if you want to look at the whole file. So just before we run the script, because I had set up these scripts for you guys, these are the Slurm scripts that we're going to be submitting to a simulated Slurm job scheduler. And so I just want to show you what this looks like. And so we're going to use that cat command. And then you guys can just copy and paste on this. So if you remember, we set up a bunch of aliases. One of the variables. One of the variables that we set up is called processing. So that's one of the ones that you can see here. You see processing here. That's just a path to where I have all the processing scripts that we're going to be submitting to the job scheduler. And so, scrolling back down here. So I'm just calling that path. And then I set up my scripts in a similar way to how I set up the output data structure. So basically in my processing directory, I have a subdirectory for each level of process data. And within that subdirectory are all the scripts that I use to run the commands that are used to generate the data. And so let's go ahead and copy and paste this. And anytime I write a Slurm script, I end it in the extension .slurm. It's really just a text file, but just to remind me that set up as a Slurm script. And so I want you guys all to add a code block and run this command. And what you see here, this should look incredibly familiar. It should look just like this because it's the same thing. So this is the Slurm script that we went over in the lecture. And this is just the exact Slurm script that we're going to be submitting to run fast QC on all of our raw data. So just as a reminder, everything up here are SBatch commands. If you want to remember what each specific option is, in the interest of time, I'm not going to go over every single option, but if you're curious, you guys can pull up the lecture and I define every single option in there. And so, and I have these extra little things to tell it to use the current profile, to tell it what I'm doing here. So I'm running raw fast QC on data from GLDS 104. I put some code in there for timestamps of when we start. I put some code in there to tell me what server things are running on. I put some code in there to tell me what number in the job, right? Because this is an array job. It's an array because we have 12 samples. So we're running the same command on all 12 samples. And so I want to make sure that it's going in the right order. I want to make sure that I'm activating the location of where the tool is that I want to use. That's what that command does. And I give it shortcuts for where the input files are and where the output files are going to be stored. And then here's where I define that variable that's going to change with each sample depending on what job we're in the 1 through 12. I also like to echo out what sample is being run, again, to make sure that this line, so the Slurm array task ID, which is going to be a number 1 through 12, is matching up with the order of the samples that I have listed in my samples.txt file. And then I always print out the version of the tool that I'm using. And so I run this command from fastqc. And again, if you didn't know what the command is to indicate the version of the tool that you're using, you could run your fastqc -- help and it'll tell you that, or you could scroll up if you guys still have that up. And then I have the actual command. So this is the actual command being run in the script. And again, that matches exactly the command that I wrote up here. So that's the command being run when we submit this script. This is just to, I hold my command in a variable too, so that way I could echo my command in my standard out, meaning that I could print my exact command so I could see what it looks like to help with troubleshooting in case something goes wrong. Then I just add a space here just to space out my standard output. And then I run this eval command, which is actually going to run the call. And then I have a bunch of commands here that's just going to tell me the total, how long the job took. And so now that we've gone through this Slurm script, we're all going to run it. So in order to run a Slurm script, it uses a command called SBatch. So SBatch is a tool to submit Slurm jobs to the Slurm job scheduler that, again, we've simulated in this environment. So you guys can all go ahead and run that. And then what it tells you is that it submitted a job to the job scheduler, and then it gives you a job ID. And then if this were an actual Slurm job scheduler, so remember, we just simulated all this. But in real life, if this were on a cluster with a Slurm job scheduler, that job ID you can then use to track the progress of your job. So this is exactly what it looks like when you submit on a Slurm job scheduler. And it is 11 o'clock. So it is our lunchtime, but when we get back, we are going to, I already had this, so good, we already went over, I forgot that I put this in there. So we already went over what that Slurm script looks like up here. So if you wanted to run that, you're just going to print out the same thing. I forgot that I added that there. And then when we get back, we're going to take a look what that standard output looks like. So go ahead, take an hour for lunch, and I want everyone back here by noon Pacific time.